In this video, we want to talk about measurable functions and generators of sigma algebras, specifically a theorem that will allow us to more easily test if a function is measurable if we have a generator of the relevant sigma algebra. Let me show you what I mean. So here we have the definition of a measurable function, or more specifically an a1, a2 measurable function. So we have two measurable spaces, omega 1, a1, we have that pair, and we have the pair omega 2, a2, and again those are measurable spaces. And you'll recall that omega 1 and omega 2 are both simply sets, and a1 and a2 are sigma algebras over those sets. And now we're dealing with the function f from omega 1 to omega 2. If we want to show, normally, whether this function f is measurable or not, then we need to test every element of a2 and see if its pre-image under f is in a1. And if that is the case, then f is said to be a1, a2 measurable. Now in this video, we want to prove a theorem that will lessen our burden in having to test all of these elements. So let's take a look at that. So this here is just the definition we just talked about above, and this theorem is what we want to prove in this video. Here we have an additional point of information. We know that the set C is a generator of the sigma algebra A2. So we didn't have that information up here with the definition. Now we have a set C that is the generator of A2. And all we're going to have to do to prove the measurability of f is just to test for each element of C if the pre-image under f is in A1. Okay, so now we're only having to test the elements of C instead of all of the elements of A2. Now let's briefly talk about what it means that C is a generator of A2. So C being a generator of A2 just is the same thing as saying that A2 is the smallest sigma algebra that contains C. So for example, I have the set C, and then maybe I determined that that is not a sigma algebra itself. Maybe it's missing. All sigma algebras have to be closed with regard to complements, right? So maybe a complement is missing and I add that in there. Or maybe something else is missing. In any case, I want to create a sigma algebra out of that, and I call that sigma algebra sigma C. That is the smallest sigma algebra containing C. And what we're saying here is that sigma of C is equal to A2. Now when I say smallest, I mean smallest with regard to inclusion. That is, if there were some other sigma algebra, for example A prime, that also contains C, then it would have to be the case that A2 is a subset of A prime. It could also be equal to it. Okay, that's all I mean by smallest. Okay, so this is what we're going to want to prove in this video. So how are we going to do that? Well, let me give you a rough draft. We want to prove the measurability of f, right? So at the end of the day, what we really have to prove is that for all A2 in the sigma algebra A2, it is the case that the pre-image is in A1, right? That's what we actually have to prove. But we're going to go about this the following way. Let's just say this is your rough draft. Let's take a look. Let's define this set here. Let's call it C bar. Let's say this is comprised of all the subsets of omega 2 for which it is the case that their pre-image with regard to f is in A1. So this set, all of the members of this set have the characteristic that we would like to be true for the elements of A2, right? All of their pre-images are in A1. And you could call this collection here, C bar, you could call that the collection of all the good sets, that is, those sets that have this characteristic that we want. And in fact, this method of proof itself that we're about to use is often referred to as the good set principle. So, what we're going to want to do is to show that A2 is a subset, it could be equal, a subset of C bar. And if we've succeeded in that, then we will have succeeded in proving the theorem, because we will have shown that all the sets in A2 are indeed good sets. That is, they all have pre-images under F in A1, which is exactly what we have to show. So now let's look at a somewhat, let's call it a somewhat less rough draft. So now what I'm going to do is I'm going to insert some stuff in here, because being able to prove that directly is not going to be so easy. So let's put some steps in there. Let's say, this is what I want to show. A2 is equal to sigma C, and that is a subset of sigma of C bar, and that is equal to C bar. Now if I could show that, then again we have A2 being a subset of C bar. But there's a bit there that we're going to have to prove, right? We're going to have to prove this, and this, and this. So let's take a look. Now, how can we prove that A2 is equal to sigma of C? Actually, we don't have to prove anything there, because one of the prerequisites in this theorem here is that C is a generator of A2. And as we said before, that just means sigma of C is A2, right? Which is exactly what we said here. So that is already true. Now what about this here? Why would it be the case that sigma of C would be a subset of sigma of C bar? Well, let's think about this. If it is indeed the case that the pre-image of all C in calligraphic C under F is in A1, that is, if this is the case, then F is A1, A2 measurable. So if this is the case, then I should be able to use that in our proof, right? So let's write that down here. We know this, that the pre-image of C is in A1 for all C in calligraphic C, right? But we also know that this set that we've defined, C bar, contains all the subsets of omega 2 for which that is the case. So it must be the case that C is a subset of C bar. Now, if we take C and we either leave it the same or add something in order to make a sigma algebra out of it, then we get sigma of C, so the smallest sigma algebra that contains C. Now, this sigma algebra here contains all the elements of C, and if we now add to that all the elements of C bar, which, I mean, they could be equal, but C bar might contain more, then obviously we're going to have even more elements in this sigma algebra here, and perhaps we've even gone overboard and added some things that make it not be a sigma algebra anymore. which puts us in a position of maybe even having to add more elements in order to make this new construction here a sigma algebra. So it becomes clear that sigma of C is definitely a subset of sigma C bar. And that's exactly what we see here. So that's also true. That's not difficult to show. It turns out that this is the crux of the matter here. This equal sign here. What are we saying? Actually, we're saying that sigma of C bar is equal to C bar. What does that mean? That means that C bar itself must be a sigma algebra. Because if we take C bar and we use it to generate a sigma algebra and we end up with C bar, then C bar must have been a sigma algebra to start with. So we're going to have to prove, in other words, that C bar, this good set that we talked about before, is itself a sigma algebra. So that's what we want to prove now. To show C bar is a sigma algebra. And if we can succeed in showing that, then we'll be done with our proof. So sigma algebra has three characteristics. C bar is going to have to contain the base set. C bar must be closed under complements, and C bar must be closed under countable unions. So let's just show these 3 points and we'll be done. So we'll start with number 1. C bar must contain the base set. Okay, what is the base set if we're dealing with C bar? We're dealing actually with this set here, right? Omega 2. So what we need to show is that omega 2 is contained within C bar. That's what we want to show. And if we think about what C bar actually means, right? C bar contains all of the subsets of omega 2 for which this is the case. Okay? So the pre-image of all those subsets has to be in A1. So if we want to show that omega 2 is in C, in other words, we can just show that the pre-image of omega 2 under F is in A1, right? That is the defining characteristic of C bar. So that's what we want to show. Now, as we did before, when I was showing the rough draft of what we wanted to prove, I'm going to insert some steps in here. Instead of showing that, I want to insert actually just one step. I say that this is the case. Now I have two things I have to show, of course. I have to show this and this, but if I can, then I will have succeeded in showing this. So, is omega 1 an element of A1? Well, A1 itself is a sigma algebra, right? So it has to contain its base set. And A1's base set, as we can see here, is omega 1. So, indeed, omega 1 is in A1. Now, is this the case here? Is the pre-image of omega 2 under F indeed omega 1? Well, let's think about that. F is just a function from omega 1 to omega 2, which means if I take any elements of omega 2 that have been mapped onto by f, then they must have come from where? From omega 1, right? In other words, the pre-image of omega 2 is omega 1. So that is indeed true. Get a check mark for number 1. Now we need to show that C must be closed under complements. And now that we know that omega 1, or that omega 2 rather, is in C bar, we can talk about complements. So here's the second part. We need to show, so first of all we'll say let A be an element of C bar. Then what we need to show is that omega 2, let's say without A, is still in C bar. And again, if we think about the meaning of C bar, then we could say this. In other words, the pre-image, now this is just the thing that has to be true in order for this to be in C bar, the pre-image of omega 2 without A is in A1. Okay, so that's what we want to show. And again, what we're going to do is I'm going to insert something in here, which is going to be easier to prove than just this in and of itself. I'm going to say, I'm just going to first of all rewrite what I see there. I'm going to say that that is actually equal to this, and that is in A1. Okay, so whereas before I only had to prove one thing, now I have to prove two things, but I'm going to be able to do that. So let's start here again. We know from before that the pre-image of omega 2 is in A1, and indeed it is omega 1. Right, that is just omega 1, and that is certainly in A1. And our prerequisite here was that A be in C bar. So that means A's pre-image under F is certainly going to be in A1. So that's in A1. And since A1, again, is a sigma algebra, then it's closed under complements. And here we have the base set and one of the elements in it. So whatever comes out of that must itself be in A1. So again, this is true. Now we just need to talk about this one here. Is that the case, that this set is equal to this set? Well, let's take a look. Let's say that some element x is in this first set here. So let's talk about what that even means. Well, if x is in the pre-image of omega 2 without A, then all that's saying is, and we know this because of the definition of pre-image, all that's saying is that if we take f of x, we're going to end up in omega 2 without A. Right? That's just a definition. Now, what else do we know? Well, if f of x is in omega 2 without A, all that means is that f of x is in omega 2 and f of x is not in A. Right? That's just a definition of this set minus here, right? That's all that is. Now, what can we draw out of that? Well, if f of x is in omega 2, then that means x must be in the pre-image of omega 2. Right? Again, just a definition. That is the definition again of pre-image. And similarly, that means that x is not in the pre-image of A. And maybe you see where I'm going with this. And now again, if I just use the definition of the set minus here again, then that just tells me that x is in f to the negative 1 of omega 2, so it's in the preimage, without this preimage. So if x is in this, then it's also in this. And since all of these arrows go both ways, I have shown that these sets are indeed equal. So that part of the proof is also complete. Part 2 gets a check mark. Now, part 3. C-bar must be closed under countable unions. Okay, so let's do that, and then we're done. So, let's take a look at this set here. Let's say all of these AI are in C-bar. And what we want to show is that the union of all of these elements is also in C-bar. And again, if we think about the meaning of being in C-bar, all we're basically wanting to show here, so I'll write in other words, is that the preimage of this union is in A1 again. And again, that's what I want to show. I don't know how to do it, so I'm going to insert something at this place, and instead I'm going to prove two things. I'm just going to rewrite, first of all, what we have over there. That's going to be equal to this. This is what I'm asserting here. Okay, so is this indeed true? Well, we know that each one of these preimages of all these AIs, they must be in A1 because they're in C-bar, right? So all of these here are in A1. And then we have a countable union of them. So since A1 itself is a sigma algebra, then the countable union of these elements must also be in A1. So this is indeed the case. So the last thing we really need to show is this here. Is this really the case that these two sets here are equal? So again, we'll just take a look. What does it mean to be in this set? So if x is in this preimage, that just means that if we take f of that x, so f of x, then we are in this union here. That's all that means, and that's how do I know that? I know that with the definition of preimage. Now, what does that mean? Well, that means, if f of x is in this union here, then one of these i's, let's call it I naught, one of these AIs must contain f of x, right? So that means there is some, let's call it I naught, so that f of x is in a I naught. And how do I know that? Well, that's just the definition of union. So now, again, I can use the definition of preimage and just say that's the same thing as saying this. If f of x is in a I naught, then that means x is in the preimage of a I naught. And again, that is just the same thing as saying that if I'm using here the definition of union, that x is in the union of all these preimages, of all these AIs. Right? If it's true for one of these x's that it's in a preimage, then it must be in the union of all of these preimages, right? So again, we've shown that these two sets are the same, and that's exactly what we wanted to show. So altogether, we see that we've shown now that this equal sign here holds. C bar is itself a sigma algebra, which means that this chain of reasoning here is true, which means that our original plan to show that A2 is just a subset of C bar worked out. And since C bar is the collection of good sets, that is, the collection that contains all the sets with the characteristics that we want, namely that their preimage is in A1, and A2 is a subset of that set, then f must be a measurable function.